Welcome to this session. In this session, I'm going to discuss numerical integrations. Okay, let's consider this equation. Okay, the equation is saying that v of f is equal to summation of ai's, then the functional value f of ai's, which is equal to a naught, the functional value of a naught, a1, then the functional value of a1, and an to an, then the functional value of an. Then, if you are given an integral, let's say I, which is equal to integral from a to b, then f of s ds. In numerical quadrature, we are saying that you can easily integrate this by using numerical integrations. That is, it will be of the form vf plus e of ef. So this is the formula for numerical quadrature, or the formula for numerical integrations, and we call this ef to be truncated error, and si I equal to 1, I equal to 0 to n is the nodes, quadrature nodes. Alright, the next section we are going to look at is numerical quadrature techniques. The first technique is trapezoidal rule, which is also known as the trapezium rule. It says that when you're having an integral, let's say a to b, a function f of s ds, you can use numerical integration. You can do numerical integration on this thing to approximate this integral to h, which is a step size, divided by 2 times the first functional value, which is f naught, plus 2 times f1 plus f2 plus f3 plus dot 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 plus fn minus 1 plus fn. He's saying that if you have the first functional value, which is when I is equal to 0, you're going to have s naught. So the functional value at s naught, which is f naught, plus 2 times the rest of the functional value up to the n term plus the n term will give you the trapezium rule. And the error term, which is ef, or the truncated error, is giving us minus xn minus s naught. So minus sn minus s naught, and the step side using the power 2, then you differentiate the function itself with 2 times, then you pick a certain small epsilon, then you divide it by 2. So this will be the truncated error for the trapezoidal rule. Now let's move to the next technique, which is known as the Simpson-Mantel. The Simpson-Mantel is saying that if I have an integral, let's say integral from a to b, f of s ds, is giving us the step size divided by 3, then the first functional value is f naught plus in any we are going to use this index, which is 0, 1, 2, 3 up to 4, 5. So if the index is odd, we multiply it by 4. So 4f1 plus 2. When it is even, we multiply it by 2. So 2f2 plus 4f3 plus 2f4 plus dot 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 until you get to the end term, which is the last index, which is fn plus fn. So this is the formula for the Simpson onetable. And the next technique we're going to look at is Simpson's 38. And it's also say that if I give an integral, let's say integral a to b f of s ds, the same as 38 of the step side into bracket, then the first functional value, which is f0, plus 3 times the rest of the functional values. Let's say f1 plus f2 plus f3 plus dot 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 plus fn minus 1, then plus the last entry fn. So this is the Simpson 38. So if you are giving this is the numerical quadrature techniques are going to use in solving the integral. When they give you an integral equation, these are the techniques you are going to use in solving them. So let's continue by using numerical quadrature to solve, let's say, freedoms. Freedom integral equation. So we are going to use numerical quadrature to solve Freedom's integral equations. So let's assume that you are given a Freedom's integral equation of the second kind. Let's consider that. Let's say y of s to be equal to lambda integral from a to b, k of st y of t dt plus f of s. We are going to use the numerical quadrature to solve this integral equation. You can really see that there's an integral here. Then we need to approximate this integral using the numerical quadrature. We're not going to use the analytic form again. We're going to use the numerical quadrature. Now, we stated at this side that we are giving I to be equal to a to b, f of s ds is equal to v of what? F plus what? E of f. And we said this is the what? Truncated error. The same thing appears here. The same thing appears here. So we have this. We have an integral of a to b, k of st, y of t, dt. So we can use numerical integrations. So if we use numerical integrations, I'm going to have here to be v of what? The whole of this, the function here, where is k, the kernel k of st, then multiplied by the ordinary function y of t, plus 8 what? 8 error, truncated error, which is k of st, then y of t. And we know that the VF, we know that VF is giving us summation of AI, f of AI, where I runs from what? 0 to what? N. So if you drop this truncated error, you can easily see that integral from a to b, k of st, yt, dt it should be approximate to what? The v of f. Then so the v of f is the same as what? This kernel. So v of k of st y of t, y of t. And from this side, you can write our v of f as v of k of s, k of st, y of t as, which is equal to the summation of, since there are two indexes, we name here as I and give an index to this as j. So let's sum it from j to be equal to 0 to n, because we are integrating with respect to t. So with the j, we are summing from j towards 0 towards n. So it becomes k of si, then tj, comma, close bracket, then y of tj. Now we can easily substitute this into the Freedom's integral equation to this side. Now replace the integrals here. Replacing the integrals, our s becomes I, is being indexed with I, which is called lambda. Then you replace the integral with what? The whole of this. Summation of j to be equal to 0, n. Then k of si, tj's, then y of tj, and then the t becomes del t. So changing t becomes changing t. So plus f of s becomes plus f of si. So let y of si to be equal to yi, and this side k of si, tj to be equal to kij, and f of si to be equal to fi. And from this side, you know that this y of t and y of s are the same function, but they are just changing what variables. So we can say that what yi and what yj are equal. So we are going to use it interchangeably. If I don't use the y, I will use the yj's. Yes, it's still the same thing. All right. So if you substitute them into this equation, you're going to have yi to be equal to lambda what? Summation. Let's send this to the other side. And you're going to have y of I minus lambda kij, yj delta t equal to f of fi. And these are just indexes, so you can just change this index j to I, and we should add connected delta function to this side. Delta ij yi minus lambda k ij, then yi delta t f of I. Now let's substitute. Let's bring yi's out. Now delta ij minus the lambda kij, then delta t yi, which is equal to fi. And so if you are able to solve, if you check the determinant of this matrix, this is a matrix. If you check the determinant, of this matrix, and it's not equal to 0, then you can generate a system of linear equations and solve for our iterative solution for the yi's. And so after finding for the iterative solution, you can combine it to solve for the solution to find for y of s, which is the solution to the integral equations.